Welcome to another video. In this video, we want to see binary representation of B+Tree nodes and some code examples. In previous lessons, we learned that each B+Tree node has two types. It can be internal node or a leaf node. So if we have a tree like this, the nodes in the last row are leaf nodes and previous ones are internal. Another point that we need to remember is that if we have a tree of degree 4, then each internal node has 3 keys, and each key has a pointer to the child in the left or right. But the leaf node with degrees 4 has 3 keys, and each key has a single pointer to the location of the data on disk. Let's begin with understanding pointer binary representation first. We know that there are two types of pointers. A pointer is either pointing to another node, which then it is used in internal nodes, or it is pointing to data on disk. So types are node and data. Second, we would want to know the position where that data or a node is on the disk. Third, we want to know which chunk is that data stored in. And we will come back to this position and chunk later because there is a lot more that we need to know about them. But for now, we assume that a position is type long, the chunk is type of integer, and the type is a single byte. Therefore, the binary representation of a pointer is 13 bytes. The first byte is type. The next 8 bytes is the position. And the last 4 bytes is the chunk. I should also mention that it's a good practice that if we are representing some sort of data in binary, we can use a version flag. And this version flag can help us if we need to parse this binary data in different way in future. But in my current implementation, I'm not using any versions. So here is the code of the pointer class. In this section, we have type, position, and chunk. The total size of a pointer is 1 byte plus number of bytes in a long and number of bytes in an integer. And if it's pointing to a data, the flag will hold the number 1. And if it's type node, the flag will hold number 2. Also, if we have a byte array and we want to start reading the pointer from a position in that byte array, again, the type would be the first byte from that position. And then we can parse 8 bytes for position and 4 bytes for chunk, which are long and integer respectively. So first thing, we need to know if a node is actually an internal node or not. Therefore, we need 1 byte for a flag. And this flag can tell us two things. First, if a node is root or not. And second, the type of the node, which again is either a leaf or internal. Therefore, this flag is also used in binary representation of a leaf node. After this 1 byte of flag, things get a little bit more complex. We know that the next bytes should be combination of pointers and keys. So it will start with a pointer. But then there will be two questions. First, we know that any comparable data can be used as a key in B+Tree node. So the question would be, what's the type of the key in our B+Tree? And again, it should be comparable. And second, what is the degree of our tree? So if we assume that the type is integer and the degree is 3, we know that integer takes 4 bytes, and as a result, our representation would look like this. The first pointer points to the node that holds keys less than the key 1. Then we have key 1. The next pointer points to the node that holds keys between key 1 and key 2. And this goes on. In the end, we will store some padding, and I will explain the reason of that later. Before we move on to discuss leaf nodes, let's a little bit know more about this flag. So the concept that we are using here is called bitwise flags. We can assume that the flag representation of an internal node has first bit as 1, then leaf nodes has second bit as 1, and the root has third bit as 1. So if we have a node that is root and is type of leaf, then the representation would look like this. If it is a root and it's internal node, then the representation would be like this. A node that is not root and its type of leaf, its representation would be like this. An internal node that is not a root would look like this. So basically this abstract tree node class is how I represent a B+Tree node. You can see it has a generic type k, which is comparable, and it is used for key. Again, the structure is described in the comment above the class. So the main idea is that if we have a byte array, then using this class, we should be able to understand its type and convert it to either a leaf node or an internal node. And if I click here, so you can see implementations of abstract tree node or the classes that extend from abstract tree node, you can see an internal tree node here and a leaf cluster tree node. There are still a lot of details that are not described yet. For example, this immutable binary object wrapper. But for example, we should now be able to understand how this isLeaf method works. It uses bitwise operation to check the flag, which is the first byte of the data. The same thing happens in the getType method. We use and bitwise operator again in isRoot method. And if we want to set or unset, we again use and or. So again, these were all topics of bitwise flags, and it's a pretty straightforward operation. I encourage you to look it up if you don't know about it yet. And the rest of the methods in this class are respectful to the degree of the tree and the value size, which I will explain later. In order to get list of the keys or iterator of keys, set a key or remove a key. Now that we understood binary representation of an internal node, binary representation of a leaf node should be very easy for us. Again, we need 1 byte for the flag, and there may be some padding in the end. And these questions will also apply to the leaf node. But instead of starting with a pointer, we will immediately start with the key 1, which again, if it's integer, is 4 bytes. and then a pointer, key 2, pointer, key 3, and last pointer. And of course, these pointer types are data, and each pointer is paired with a key. In next video, we will see how we can read and write this binary data on disk. And we will understand more about this position and chunk in a pointer, and also the padding at the end of each node. If you enjoy the contents on this channel, don't forget to like and share. And to get notification for next videos, consider a subscribe. See you in next video and take care.